Question 1. In this question, we have to collect the definitions and simple properties of some stochastic processes. The first one is the Poisson process. The definition of Poisson process is the number of the points ti in the interval from t1 to t2, the probability that nt1 t2 equals k equals e to the power of minus lambda t times lambda t to the power of k divided by k factor. That's the definition of the Poisson process. The properties of the Poisson process are: first one, if the interval t1 t2 and interval t3 t4 has non-overlapping, that means nt1 t2 and nt3 t4 are independent. Now we have to figure out the probability mass of the Poisson process. That should be pxt equals k equals e to the power of minus lambda t times lambda t to the power of k divided by k factor. That's the probability mass. And the mean of Poisson process is simply ext equals lambda t. Then the autocorrelation function, rt1 t2 equals lambda squared t1 t2 plus lambda minimal of t1 t2. That's one of the proof in the previous homework. We have already proved it. Then the autocovariance function, ct1 t2 should be simply lambda times minimum of t1 t2. Then the discussion. From the mean of the Poisson process, we can find that the mean of Poisson process is lambda t and it's a linear function of t. And we think it's quite reasonable because the longer time we wait, the expected value of buses is larger. And also, the autocovariance function of Poisson process is simply equals to the autocorrelation function of the Wiener process. That's quite interesting. Now we have to discuss the Poisson increment process. The Poisson increment process is defined as yt equals to xt plus epsilon minus xt divided by epsilon. And in this case, xt is Poisson process. Then the probability mass of the Poisson increment process is pyt equals n divided by lambda equals e to the power of minus lambda epsilon lambda to the power of n divided by n factor. Then the mean of Poisson increment process is simply lambda. When it comes to the autocorrelation function, r y t1 t2 equals lambda when t1 minus t2 absolutely larger than epsilon, or equals to lambda squared plus lambda divided by epsilon minus lambda times absolute value of t1 minus t2 divided by epsilon squared when t1 minus t2 less than epsilon. Then the autocovariance function, cy t1 t2 should equals to 0 if t1 minus t2 larger than epsilon, or equals to lambda divided by epsilon minus lambda times t1 minus t2 absolutely value divided by epsilon squared when t1 minus t2 is less than epsilon. Now the discussion. we can simply notice that the Poisson increment process is introduced to prepare us with the Poisson process. They have some kind of related. And one interesting fact is that the mean value of the Poisson increment process is constant. Then we have to discuss the Poisson impulse. The definition of Poisson impulse is defined as Zt equals to d by dt times xt when xt is a Poisson process. Then the mean of the Poisson impulse is EZT equals to lambda. That is the same as the Poisson increment process. The autocorrelation function RZT1 T2 equals lambda squared times the plus lambda delta T1 minus T2. And the autocovariance function CZT1 T2 simply equals lambda times delta T1 minus T2. Then the discussion. From the mean and autocorrelation function of the Poisson impulse, we can simply know that the Poisson impulse is a WSS process since it has constant mean and autocorrelation function of T1, T2 is only related with tau, which is T1 minus T2. Moreover, when we discuss the ZT minus lambda, we can easily find that if we have defined a process Wt to be ZT minus lambda, it has zero mean, and the autocorrelation function of Wt simply equals to lambda times delta T1 T2. In this case, we can find that Wt is a white noise. Then the fourth, semi-random telegraph signal. The definition of semi-telegraph signal xt is defined based on Poisson points. We can note that the probability that the number n in the interval from t1 to t2 equals to k equals e to the power of lambda t divided times 2 to the power of k divided by k factorial. And in this case, xt equals to 1 if k is even, or xt equals to minus 1 if k is odd. Then the probability mass pxt equals to 1 equals e to the power of lambda t times e to the power of lambda t plus e to the power of minus lambda t divided by 2. Then pxt equals to minus 1 simply equals to e to the power of minus lambda t e to the power of lambda t minus e to the power of minus lambda t divided by 2. The mean of ext is simply e to the power of minus 2 lambda t, and the autocorrelation function of Rx t1 t2 simply equals to e to the power of minus 2 t1 minus t2, and autocovariance function Cx t1 t2 equals e to the power of minus 2 lambda t1 t2 absolutely value minus e to the power of minus 2 times lambda t1 plus t2. Then the discussion. From the probability mass function, we can simply notice that the probability xt equals to 1 and xt equals to -1 is not half, because we started by the semi-random telegraph process by 1. So I think the probability of xt equals to 1 should be a little larger than 1 divided by half. And moreover, if t equals to infinitive, then the probability of xt equals to 1 should have no difference with the probability of xt equals to -1 should be 1 divided by 2. Then we have to discuss a similar process, that is the random telegraph process. The random telegraph process is divided as yt equals to a times xt, and also the probability of a equals to 1 equals the probability of a equals to -1 equals to half. In this case, xt is semi-random process. The mean of yt simply is 0, and the autocorrelation function ry t1 t2 equals e to the power of -2 lambda t1 minus t2, and the autocovariance function cy t1 t2 equals e to the power of 2 lambda t divided times t1 minus t2 absolutely value. Then we have to discuss the random telegraph process. As is shown in the probability of random telegraph process, we can think that the random telegraph process has more freedom or randomness than the semi-random process, because the probability of a equals to 1 and equals to -1 are also 1/2. And moreover, given by the mean of the yt and the autocorrelation function, we can know that the random telegraph process is a WSS process. And moreover, the autocorrelation function and the autocovariance function are the same. So in this case, we may guess that the random telegraph process may also be a strict sense stationary. Then the sixth part, the random walk. The definition of random walk is defined by we toss a fair coin n times, and k is the number of heads, where n minus k is the number of tails. So in this case, we have xnt equals xt equals to cnn plus r divided by 2 times 1 divided by 2 to the power of n. I'm sorry. Actually, in this case, xnt equals to 2k minus n times s. And now we have to discuss the first order probability mass. pxt equals to rs equals to cn n plus r divided by 2 times 1 divided by 2 to the power of n. And the mean of xt is 0. The autocorrelation function of its rt1 t2 is the minimal value of nm times s squared, and autocovariance function ct1 t2 equals minimum of nm times s squared. Then the discussion part. From the probability mass, we can know that when n is equals to infinity, this probability will become the Gaussian density, and the autocorrelation function is not depend on the T1 or T2 or T1 minus T2. It actually depends on the minimum of T1, T2. And then that should be the property of the independent increments. Then the last part, Wiener process, which is also known as the Brownian motion. Wiener process is defined as Wt equals to limit case t equals to 0, s squared divided by t equals to infinitive, and n equals to infinitive xt, where in this case xt is a random work. Then the density function of the Wiener process f Wt equals to 1 divided by 2 pi alpha t e to the power of minus w squared divided by 2 alpha t. The mean of the Wiener process equals to 0. And autocorrelation function Rw T1 T2 equals to alpha times minimum T1 T2. And autocovariance function Cw T1 T2 equals to alpha times minimum of T1 T2 as well. Then the discuss of the Wiener process is that we can know that Wiener process has a Gaussian increment since its density function is quite like the Gaussian distribution function. That's the answer of the first question. Thank you.